Hello and welcome back to our third video in our improper integral series. In this video, we are going to look at the comparison theorem, and we're going to look at a couple other applications. So let's start with the comparison theorem. Suppose that f and g are continuous functions with f of x greater than or equal to g of x, and g of x is greater than or equal to 0 for any x value greater than or equal to a. So if the improper integral from a to infinity of f of x dx is convergent, then the improper integral from a to infinity of g of x dx is also convergent, because f of x bounds g of x from above. If the improper integral from a to infinity of g of x dx is divergent, then the improper integral from a to infinity of f of x dx will also be divergent. And that's because g of x bounds f of x from below. So let's see this in action. Show that the improper integral from 0 to infinity of e to the negative x squared dx is convergent. Since we cannot evaluate this integral directly, it is not an elementary integral, we may write it as follows. The integral from 0 to infinity of e to the negative x squared dx is equal to the integral from 0 to 1 of e to the negative x squared dx plus the integral from 1 to infinity of e to the negative x squared dx. The first integral is a definite integral. There are no discontinuities at the endpoints or inside the interval. The second integral is a type 1 improper integral, and this is the part we're going to focus on. We're going to use the following facts for x greater than or equal to 1. X squared is greater than or equal to x, and this implies that negative x squared is less than or equal to negative x. And again, this will imply that e to the negative x squared is less than or equal to e to the negative x, since the exponential function is an increasing function over its domain. Now, the improper integral from 1 to infinity of e to the negative x squared dx is going to be less than or equal to the limit as t approaches infinity from the integral from 1 to t of e to the negative x dx. And this integral evaluates out to the limit as t approaches infinity of e to the negative 1 minus e to the negative t, which happens to be equal to e to the negative 1. Therefore, by taking f of x equal to e to the negative x and g of x equal to e to the negative x squared in the comparison theorem, we can see that the improper integral from 1 to infinity of e to the negative x squared dx is convergent. And because the sum of convergent integrals leads to a convergent integral, we may also conclude that the integral from 0 to infinity of e to the negative x squared dx is also convergent. In this example, we're going to determine if the integral from 1 to infinity of 1 plus e to the negative x divided by x dx is convergent or divergent. If we use the comparison theorem with f of x equal to 1 plus e to the negative x over x and g of x equal to 1 over x, we do have g of x less than f of x. But the integral from 1 to infinity of g of x dx is a divergent integral. We've established that earlier. So by the comparison theorem, we have that the improper integral from 1 to infinity of 1 plus e to the negative x over x dx will be greater than the improper integral from 1 to infinity of g of x dx. And because we were able to bound the integrand from below, we may conclude that, from the comparison theorem, we may conclude that the improper integral from 1 to infinity of 1 plus e to the negative x over x dx is divergent. A short note that will prove useful throughout the course is that the integral from 1 to infinity of 1 over x to the p dx is convergent. If p is greater than 1, it will be divergent for p less than or equal to 1. Now, the proof of this is pretty much a direct calculation, but we'll go through the details. If p does happen to be equal to 1, then we have the integral from 1 to infinity of 1 over x dx. We know that we need to back off the infinity, so we have the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. We know that the integral of 1 over x is natural log of x, so we have the limit as t approaches infinity of the natural log of x, which equals the limit as t approaches infinity of natural log of t minus natural log of 1, and this approaches infinity. So the integral is divergent when p is equal to 1. When p does not equal 1, that same integral is going to evaluate to x to the negative p plus 1 over negative p plus 1. We evaluate this over the interval from 1 to t, and we get t to the 1 minus p divided by 1 minus p minus 1 to the 1 minus p over 1 minus p. Now, as I take the limit as t approaches infinity on this, we end up with two possible behaviors. So the limit as t approaches infinity of t to the 1 minus p power, all of that divided by 1 minus p, minus 1 over 1 minus p, will evaluate to 1 over p minus 1, but p has to be greater than 1. When p is greater than 1, t will have a negative exponent, and that means that as t approaches positive infinity, that quantity is going to go to 0. But when p is less than 1, that means 1 minus p will have a positive value, and that means t will be raised to a positive power, and as t approaches infinity, the entire ratio will approach infinity as well. So the integral will converge when p is greater than 1, and it will diverge when p is less than 1. And we've already established that when p equals 1, it also diverges. So we have our conclusion. The integral converges when p is greater than 1 and diverges when p is less than or equal to 1. Now, you can have improper integrals that are of both type 1 and type 2. And when this occurs, we handle those cases individually. So if the integral from a to infinity of f of x dx is a type 1 improper integral, and if f has an infinite discontinuity at a, then the integral is also a type 2 improper integral. And if this is the case, we will apply both of our rules and we'll just rewrite the integral as the integral from a to infinity of f of x dx will be equal to the integral from a to c of f of x dx plus the integral from c to infinity of f of x dx, where c is bigger than a. And then we will take each of those integrals and use our limit notions. So that will result in the limit as t approaches a from the right of the integral from t to c of f of x dx, plus the limit as b approaches infinity of the integral from c to b of f of x dx. And we will evaluate each of these limits individually. And this is how we approach improper integrals that have both a type 1 and type 2 discontinuity. So as an example, we're going to look at the integral from 0 to infinity of 1 over the square root of x dx. And we're going to determine if this is convergent or divergent. Now, this integral has a singularity at x equals 0, but it also has an infinite interval. So we're going to split this up. We're going to take the integral from 0 to infinity of 1 over the square root of x dx, and we're going to make this equal to the integral from 0 to 1 of 1 over the square root of x dx, plus the integral from 1 to infinity of 1 over the square root of x dx. Now, the second integral has p less than 1, because the square root has a 1/2 power. So this integral diverges, and if any part of the integral diverges when I split it up, the entire integral is going to diverge. So the integral from 0 to infinity of 1 over the square root of x dx will also diverge. One of the applications of improper integrals comes in the form of integral transforms. And one of the most popular transforms is the Laplace transform. So if f of t is continuous for t greater than or equal to 0, the Laplace transform of f is the function capital F, defined as follows. Capital F of s is equal to the integral from 0 to infinity of lowercase f of t equal to times e to the negative st dt. And the domain of f is the set consisting of all numbers s for which this integral converges. So our example here is going to demonstrate the use of the Laplace transform. And we're going to determine the Laplace transform of f of t, which happens to be equal to e to the t for our example. So we're going to substitute e to the t for f of t. So we have capital F of s is equal to the integral from 0 to infinity of e to the t times e to the negative st dt. And when I do the multiplication of the integrand, I get the integral from 0 to infinity of e to the t times 1 minus s dt. Now this is a type 1 improper integral, so I back off the infinity and use the limit notion, and I get the limit as b approaches infinity of the integral from 0 to b, e to the t times 1 minus s dt. Integrating e to the t times 1 minus s leads me to the result of having the limit as b approaches infinity of 1 over 1 minus s times the quantity e to the t times 1 minus s in the exponent over the interval of 0 to b. So I have 1 over 1 minus s, limit as b approaches infinity of e to the negative b times s minus 1 in the exponent, minus e to the 0 power. We know that e to the 0 power is 1. We know that the limit as b approaches infinity of e to the negative b approaches 0, and therefore the result is 1 over s minus 1. So the Laplace transform of e to the t is equal to 1 over s minus 1. And this concludes our improper integral video series. I hope that it was helpful for you, and I thank you for your time and attention.